Hi there, how y'all doing? We are starting the last unit of material before the first exam, and that's kind of a nice marker to be at. So let's go ahead and get started. Um, this is section 2.5, which is on linear transformations. We'll start with the definition. If we have an M by N matrix, and there is no specific reason why M and N have to be different, this can be a square matrix. Can be square, but doesn't have to. And so we allow for the two numbers to be different, but they can be the same. Let A be an M by N matrix. We're going to define a function where we plug in X and we get out the combination A times X. This function will take input vectors from Rn and send out vectors in Rm, and we call this a linear transformation. As an example, if this is my matrix, 3, -2, 1, 2, 0, 3, then that matrix defines a linear transformation that we build using the column row rule. We will have an input vector that has two elements in it, x1 and x2. x1 gets multiplied by the first column, x2 gets multiplied by the second column. And so the result is the vector 3 times x1 minus 2 times x2, x1 plus 2 times x2, and 3 times x2. And so this transformation transforms this vector x1, x2 into this vector here, 3x1 minus 2x2, x1 plus 2x2, and 3x2. So not only do the numbers in the vector change, but in fact the size of the vector changes. It changes from a vector in R2 to a vector in R3. And so that's quite a transformation that's happening here. Since the input vector is in R2, but the output vector is in R3, we abbreviate that using this notation here, that the transformation T sends vectors in R2 to vectors in R3. That's what this notation stands for. All right, let's look at another example. Working backwards from that last example, here's a transformation that takes a vector in R3 and sends it to a vector that's in R2. And let's identify the matrix A that generates this linear transformation. All right. So here's the solution. If I look at what is multiplied by x1, x1 gets multiplied by -4 and 1. x2 gets multiplied by -1 and +2. And x3 gets multiplied by 2 and -1. And so if I take these vectors and combine them into the matrix -4, -1, 2, 1, 2, 1, this matrix A creates this linear transformation. So this is the matrix which generates the linear transformation. All right. What we can use linear transformations for is to achieve a range of geometric transformations of two-dimensional and three-dimensional surfaces. To do this, we're going to make a lot of use of the standard basis vectors EI, E1, E2 if we're in 2 dimensions, E1, E2, and E3 if we're in 3 dimensions. So we're going to do an example here. We're going to construct a linear transformation that rotates every point in the plane counterclockwise by 90 degrees. So we can do this, but given the hint that we have up here, we're going to make use of the standard basis vectors. So we're going to start by rotating just those two standard basis vectors. So here's our solution. We apply the transformation to the standard basis vectors. So when I take E1 and I rotate it counterclockwise 90 degrees, it's now pointing straight up. And so the coordinates after rotating are 0, 1. And then if I start with the vector E2, which points in the y direction, and rotate it 90 degrees counterclockwise, it's now pointing to the left. And after rotating, its coordinates are negative 1, 0. I'm going to make use of these coordinates on the next slide. We're going to arrange those transformed standard vectors into a matrix. And so the transformed version of E1 goes in this column. This is the transformed version of E1. And the transformed version of E2 goes into this column. So they're not the original coordinates of E1 and E2. They're the coordinates we get after we rotate them 90 degrees. And that linear transformation will rotate every single point in the plane counterclockwise 90 degrees, not just the two standard basis vectors. For example, if we wanted to look at the point negative 2, 3, so let's give this a try. So right here is the vector negative 2, positive 3. It transforms into the top number becomes a negative y, so the top number now is now negative 3, and the bottom number is now just whatever x is, so that's negative 2. Well, negative 3, negative 2 is this vector down here, and that's the same vector that you would get if you took this vector and rotated it 90 degrees counterclockwise. We applied the transformation to E1 and E2, the standard vectors, and then that matrix works for every other vector, because every other vector is a linear combination of T1 and T2. All right. So we have a theorem here. If this transformation is a linear transformation defined by this matrix, then the columns of this matrix identify what happens to the standard basis vectors in Rm. Let's do another example. We're going to construct a linear transformation that reflects every point in the plane horizontally across the y-axis. All right? So we're going to start with the two standard vectors. This is the vector E1. And if I reflect it horizontally across the y-axis, that just makes the vector negative. And so the transformed version of E1 will be the vector negative 1 in the x direction and 0 in the y direction. Now if we start with the E2 vector, well, when we reflect this vector across the y-axis, it just stays in exactly the same place. The transformed version of E2 is still the vector 0, 1. And so the matrix that generates our transformation is going to be negative 1, 0 and 0, 1. the transformed version of E1 in the first column and the transformed version of E2 in the second column. And therefore the transformation, is going to be negative 1, 0, 0, 1 times the vector xy. That's x times negative 1, 0 plus y times the vector 0, 1. And that is the transformed version, negative x, y. And so for any vector that's in the plane, the transformation moves x over to negative x, but leaves y exactly the same, and therefore it will move this vector to its reflection across the y-axis. We constructed this linear transformation by knowing only what it did to E1 and E2, but once we get it for E1 and E2, it transforms every vector the way we want it to. All right? Let's move on. Another definition, we say that a transformation is closed under addition if this formula right here works for all vectors in Rm. What this section is saying is on the left-hand side, we do the parentheses first. And so we add x and y first because they're inside the parentheses, and then we apply the transformation. Then we transform the total of x and y, or the sum of x and y. On the right-hand side, we are transforming x first, and we're transforming y second. And after we've transformed them individually, we add the results together. So on the left side, we add first and then transform. On the right side, we transform first and then add. We say that transformation is closed under addition if the answer doesn't matter, if both sides are equal. So that is, we can either add the vectors first and then transform them, or transform them first and then add them. But we get the same answer both ways. We say the transformation is closed under scalar multiplication. Same kind of idea. On the left-hand side, we're doing the parentheses first. And so I'm taking x and I'm scaling it by some constant c. After I scale it, then I apply the transformation to the result. Okay? On the right-hand side, I am transforming the vector x, and then I scale the answer after we've transformed it. An operation, transformation is closed under scalar multiplication if the result doesn't matter. Whenever we transform a scaled vector, we can scale the vector first and then transform it, or we can transform it and then scale it, but we get the same answer both ways. As it turns out, we have a theorem. All linear transformations are closed under addition and closed under scalar multiplication. Every possible linear transformation obeys both of these rules. We can transform and then add, or add and then transform. We can transform and then scale, or we can scale and then transform. And it doesn't make a difference whichever one we do. Let me give you an example of how that works. I have a linear transformation, and I know what it does to my standard vectors, E1 and E2 and E3. What I would like to know is what it does to the vector 4 negative 2, 3. Well, this is the vector for E1 plus negative 2E2. So I'll just say, right, negative 2E2 plus 3E3. But because I can transform first and then add or scalar multiply, I can do all these transformations first and then apply the 4 and the negative 2 and the 3. In other words, this answer is going to be, sorry, get back there, hit the wrong button, 4 times 3, negative 2, 1, plus negative 2 times negative 3, negative 4, 2, plus 3 times 4, 2, 1. That is, what I'm doing is I'm transforming E1 and E2 and E3 first. And then applying the 4 and the negative 2 and the 3. And that works. This gives me 4 times 3 is 12, plus 6 is 18. 18 plus 12 is 30. The second row, we get negative 8, positive 8. Those cancel. 3 times 2 is 6. In the bottom row, we get 4 and negative 4. Again, those cancel. And 3 times 1 is 3. So this very natural and obvious thing we did on this line works for all linear transformations. And once I know what happens to E1, E2, E3, I can then apply this to any other vector and get the result that I want. All right. Let's say we have 2 linear transformations. A is the matrix associated with the first transformation, and B is associated with the second transformation. Is there a way that we can compute the matrix associated with the composite transformation, T1 composed with T2? Well, by definition, T1 composed with T2 of X is we plug X into T2 first, and then we take the answer to that and plug the answer into T1. That's how composition works. But the answer to T2 of X is B times X. And the answer to T1 is to multiply that by A. And we saw way back on day 4, it was example 43, that the matrix that does A parentheses BX is the same as the parentheses going here times X. And we can move the parentheses around and not change the answer. And so the matrix A times B, which we get using the column row rule, is exactly the matrix that we want. So let's give this a try. Here's a matrix T1. Here's a transformation T1. This is a matrix A, and T2, and here's the matrix B. We want to compute the matrix for the linear transformation T1, T2. And so what we will do is we will apply the column row rule here. And that's going to give me 2, negative 3, 1 times 1, 4 plus 0, 3, 4 times 2, negative 1 plus 1, 2, 5 times 3, 0. That's what the column row rule does for us. 2, negative 3, 1 times 1 is 2, negative 3, 1. 2, negative 3, 1 times 4 is 8, negative 12, 4. 0, 3, 4 times 2 is 0, 6, 8. 0, 3, 4 times -1 is 0, -3, -4. 1, 2, 5 times 3 is 3, 6, 15. And 1, 2, 5 times 0 is 0. When we add these together, we get 5, 8. Then we get 3 and -3 and 6 is 3. 3 and 6 is 9. -12 and -3 is -15. 1 and 8 is 9. 9 and 15 is 24. 4 and -4 cancel. And then we add 0 and we still have 0. And so this matrix is the matrix that generates this combined transformation T1 and T2. We're just taking the matrix for T1 and the matrix for T2, and we combine them using the column row rule. All right. One more example. It's got a couple of parts to it, but we will wrap up in a moment. So we're going to look at these two matrices. T is generated by the matrix A, S is generated by the matrix B. In part 1, it says we write that T goes from R3 to R3. So what do we do right for the transformation S? Now this is a 2 by 3 matrix. But the definition says that B comes on the left side and because of the column row rule, since B has 3 columns, I need 3 numbers to pair them up. I need an x1 to go with the first column, and an x2 to go in the second column, and an x3 to go in the third column. And so the input vectors for S have to come from R3. When we add them together, what we're going to get is something on the top row, -2x1, 3x2, and 2x3, and something on the bottom row, 1x1 plus 1x2 plus 4x3. But this is only in R2. And so our output vectors are in R2. And so these numbers appear in reverse order from these numbers. That R3 is based on the columns and R2 is based on the rows. That's a little confusing, but this is one of the things that we just get used to and accept after a while. So a 2 by 3 matrix generates a transformation from R3 to R2. So let's do part 2. Part 2 is we're going to compute what T of 1, 2, 1 is. All right, so that's going to be 1 times the first column, and then 2 times the second column, and then 1 times the third column. Each of these numbers times each of these columns. So column, row. All right. So in the top row, we get 1 minus 4 is -3. -3 plus 5 is 2. In the middle row, we get 2 plus 2 is 4. 4 plus 0 is still 4. In the bottom row, we get 4 plus 6 is 10. 10 plus 3 is 13. So we end up with a matrix, or with a vector 2, 4, 13. And we're going to use this answer for part 3. So let's remember this, 2, 4, and 13. And move on. Question 3 says, where V is the answer from part 2, which is 2, 4, and 13. Compute S of this vector. So S is B times this. So 2 is going to get multiplied by -2, 1. This goes with the first column. 4 goes with the second column. So 4 times 3, 1. And then 13 goes with the last column. And that gives us, in the top row, -4 plus 12 is 8. 8 plus 26 is 34. In the bottom row, 2 plus 4 is 6. 6 plus 52 is 58. And so we're left with 34 and 58. And we're going to need to use this answer in the next problem. So 34 and 58, we're going to put on the next slide. We're going to compute the matrix for this linear transformation S composed with T. All right? So that is going to be B, because S comes first, times A. So B times A. So we're going to do columns on B and rows on A. So this is going to be -2, 1 times 1, -2, 5 plus 3, 1 times 2, 1, 0 plus 2, 4 times 4, 3, 3. So -2, 1 times 1 is -2, 1. -2, 1 times -2 is 4, -2. -2, 1 times 5 is -10, 5. 3, 1 times 2 is 6, 2. 3, 1 times 1 is 3, 1. And 3, 1 times 0 is, sorry about this, I have to call somebody back in a moment. There we go. Sorry about that. All right, 0, 0. And then the last matrix, 2, 4 times 4 is 8 and 16. 2, 4 times 3 is 6 and 12. 2, 4 times 3 again is 6 and 12. So we're going to add all these together. -2 and 6 is 4. 4 and 8 is 12. 4 and 3 is 7. 7 and 6 is 13. -10 and 0 is -10. -10 and 6 is -4. In the bottom row, 1 plus 2 is 3. 3 plus 16 is 19. -2 plus 1 is -1. -1 and 12 is 11. And the bottom row, 5 plus 0 is 5. 5 plus 12 is 17. And then we want to verify our matrix using the answer to part 3. So I'm going to back up just for a second. What we did was we first plugged in 1, 2, 1 into T. Then we plugged the answer of that into S, and we got 3458. So what should we do is plug in 1, 2, 1 again into this matrix. So let's see what we get. We get 12, 19, 13, 11, -4, 17 times 1, 2, 1. Column row rule. So 1 times 12, 19. 2 times 13, 11. And 1 times negative 4, 17. So that's still 1219 plus 26, 22 plus negative 4, positive 17. All right. 12 plus 26 is 38. 38 minus 4 is 34. 19 plus 22 is 41. And 41 plus 17 is 58. And so we get the same answer both ways. We can get the same answer by plugging this vector first into T, then taking the answer and then plugging that into S, and then getting the result, or by using the column row rule to combine the matrices for S and T into a single matrix, and then plugging 1, 2, 1 into that linear transformation instead. Both methods work. Both methods get you the same answer. If you're familiar with both methods, you have ways of being able to leverage this to check your work on an exam, because both methods should give you the same answer. All right? Have a great rest of the week. We will review next time and take the exam the week after. All right? Have fun.